Okay, let's get started. If you have, how many people are here? 7 people out of 20 who are here. If you have a project proposal, put it there. I haven't graded your homework 5. Research stuff came up. I didn't have time. But so I'll have homework 5 graded probably by Wednesday, and hopefully this by Wednesday too. So, any questions about the project or anything else? Yeah.
So then we're allowed to start research now.
Oh yeah, of course. Yeah, so the only real thing left in the class is the research project itself and the paper presentation, if you haven't gone yet. So yeah, go ahead, go nuts. Any other questions? Yeah. Yeah, do you have a question? Okay. Any other questions? Okay, so let's, I was going to talk about 2 different topics today. The one that's on the schedule is projection. But I realized that this is only like a mathematical curiosity. It is a nice thing. So I'm only going to briefly talk about projection, and then we'll move into some more exciting stuff. So projection is basically the idea that, so actually what have we done so far? So what we have is, let's just say if we want to get a bound like can of TKV less than or equal to something. So if you have your project proposal, please turn it in. Okay. So all the bounds that we have gotten so far are can TKV less than or equal to something. And the usual suspects are something involving, let's just say, can of TK plus 1 V, or can of TK minus 1 V, or can of TK V minus 1, or something along those lines, where we modify one of the parameters each time. And we get some kind of bound for that. So projection is the idea of increasing the number of columns by 1 and reduce symbols, or I guess number of values, by 1. So, or increasing the number of columns by a certain number and decreasing the number of values by the same number. So doing both of those things at the same time. We could phrase it in terms of the other bounds that we have, but it's not nearly as good as what projection can do. And the really, not awful, but it's just not really convenient thing, is that this only works as currently understood for t equals 2. And why is that? Because with t equals 2, it is really easy to characterize which interactions are left uncovered when we add a new column. Whereas when you have t equals 3, it's harder to characterize that. So yeah, I'm not going to talk a whole lot about this, but so here's the basic gist. Just in a picture, all of the text above is basically saying what this picture is saying. So what I did here is we have a covering array on the left side right here with 4 columns, and what I did was I standardized on 2s. So by standardize, remember, that means have a row of all 2s. And you modify the values in the columns so that you achieve that. And what do you notice here? Well, you see that every interaction that has 2 2s in it is in the last row. So if you look at, say, the second column and the fourth one, you see that there are 2 2s in that last row. Do you see 2 2 anywhere else in the entire covering array? No, it's not anywhere else. And you can actually verify this because every other row has exactly 1 2 in it. So for that reason, projection also only works when you have the 2 2 interactions appearing exactly once, namely only in the last row. So what do we do then? We strike out this row right here, the last row. So then here's what we do in addition to that. So we strike out a row and we add a new column to this. So how do we determine this? Well, let's look at the rows here. I've ordered them in groups of 2. And you can call the first group the 0 group, the next group the 1 group, 2 group, and 3 group. And then the new column corresponds to just looking at that group number and putting that value in the new column. So 0 0 because it's the 0 group, 1 1 because it's the 1 group, 2 2, 3 3. And that's how we get the array on the right, where because we're trying to reduce the number of symbols by 1, we started off with 3, we're trying to get rid of 2s and consequently 3s. So that's why this array on the right corresponds to changing all of the 2s and 3s to don't care positions. And that's how we obtain the array on the right. So what we can gather from this is that the can of 2, because we're always dealing with strength 2, k plus 1 because we added a column, v minus 1 because we removed one of the values, is at most, well, take the covering array on the left, which is 2kv, the original one, minus 1, because we were able to strike out that last row. And it is possible to extend this by introducing a whole set of new columns and deleting a lot of values, but you have to guarantee that the value that you're deleting appears exactly once for every pair. So in the original one, we guaranteed that the 2 2s appear exactly once, so we can delete them. But say like a 1 1 in the original, it does not appear exactly once, I think. Is that true? Does 1 1 appear multiple times? Yeah. So like in the array on the right, if you look at the first 2 columns, we see 0 0 1 1 appear multiple times. So we can't do the same thing for the resulting array. But there are certain arrays for which you can actually extend this arbitrarily, which are called orthogonal arrays. So I'm not going to deal with that. So that's all I'm going to really say about projection. If you want to explore this type of idea in addition to whatever you're doing for your project, that's also a good idea. There's a lot of open questions here, but I'm just going to leave it at a high level. Any questions about projection? Yeah. Oh, I thought you had. Yeah.
So you're basically using projection so to start it, you would have to have an array with, say, the same TKB except k minus 1 or k plus 1, and the goal, or k plus 1, and the goal would be to minimize one of them so that you have the ideal amount for TKB.
Yeah, so note that t has to be 2 here for this to work, or for what is currently understood. It could work for t equal 3 and above, but only t equals 2 works for what we know. And you have to guarantee that every pair with a certain value appears exactly once. Otherwise, this method does not work, or at least doesn't work in this particular way. Sorry, what was your question?
My question was, so you take, so to find like the ideal value for some TKV covering array, you just take another covering array with some specification bumped up or bumped down.
Yeah.
And then you, like for those v plus 1, you would just turn all
Right, yeah. So let's just say that you're trying to minimize the 2k plus 1 v minus 1 for whatever parameter set that you want. Then what you would do if you wanted to apply this method was to find an array with 2kv such that every pair with a certain value appears exactly once, and then you get this bound out of it. But it turns out, well, we don't know if we can make the -1 into a -2 or anything, and that's all that you can really guarantee out of this. There are other techniques that you can look at the resulting array and then make some calculations on top, but without any additional information about the array itself, we can't guarantee anything. But there are ways that you can extend this. But yeah, so it's very restricted in what it can do, but for what it can do, and for orthogonal arrays, which are arrays where every interaction appears exactly once, this is a very good method. And actually, some of the best bounds come from this too. Any questions? Yeah.
Can you explain the theory again? I'm a little bit confused here.
Yeah, so I'm not going to explain the entire reason why this is the case, but so in the original array, we're standardizing on the 2's here. So then the method says delete the row of all 2's. And then in the original array, what we're going to do is we're going to group look at the first column where the 2's are, and I'm going to put all of those into one group. So notice that the 2 rows up here, so these 2 rows, have a 2 in the first column. So I'm going to group them all together. And then I'm going to group all the rows that have 2 in the second column and put them all together. So I'm going to form these groups right here. And what do I do? Well, for the first group, I'm just going to put all 0's with a new column attached to it. And then for the next group, I'm going to put all 1's. Next group, I'm going to put all 2's. Next group, I'm going to put all 3's. And because we had 3 values before, 0, 1, and 2, and I took away the row of all 2's, well, now I want an array on 0's and 1's only. So then in the resulting array, the middle one here, I guess I didn't really fix it, but the 2's and the 3's, I'm going to change into don't care positions because I don't care what they are. And then in the final array, you can change those to be 0's and 1's, however you want. Yeah.
Is it by chance in this example that all the groups have the same size?
Yeah, it just happened to be that they're all the same size, but it's not necessarily true. There is a conjecture about how often symbols can appear in a covering array, but that conjecture is not proven, so we can't really guarantee that they'll all be the same size or whatever. Other questions? Okay, so let's actually talk about a new topic. So how many of you have ever heard of metaheuristics? So the basic idea for those who haven't heard it is an algorithm that tunes its behavior depending on how well it does. So if it does really well, then it changes its parameters so it doesn't like overshoot the best what it's targeted at doing. But if it's not doing very well, then it does some drastic changes to try to get a better result. And how many of you ever heard of the Gecko Conference? It's a really cool conference. So the G here stands for genetic algorithms. And what it is just a giant conference where a lot of people talk about metaheuristic algorithms for solving various things. So like if you're interested in software engineering and you want to apply genetic algorithms to it, or if you're trying to optimize some algorithm with genetic algorithms or metaheuristics, as we're going to see, this is a great conference. So if you're interested in this sort of thing, Gecko is definitely a good conference to go to. And in fact, I submitted a paper for this year, and I had one accepted last year. So it's a really good conference. So here's the basic idea. So what we're trying to do is, here's the basic idea. So we have some kind of function, f of x, and we want to find an x such that f of x is maximum or min or something. So we have some function we want to optimize, whether we want it to be the largest possible or the minimum possible or whatever. So we're trying to optimize this function. So in the context of what we're doing, we have an array, and it may or may not be a covering array. And the function here, or one function you may want to optimize is, well, look at the number of interactions that are not covered by this array. Well, if that number of not covered interactions is 0, then you have a covering array on your hands. But if you have some interactions left uncovered, then it's not optimal necessarily. So what we're going to define here is what is called the deficiency. And it's the number of uncovered interactions. If you have 0 of them, you're done. But if you don't, the whole idea behind metaheuristics is, if we have some number of uncovered interactions, let's just change the array a little bit and just see what happens. If we make a good change, great. If we don't, well, maybe we shouldn't do that change. Okay, so maybe if I change this 0 to a 1, maybe it becomes a covering array. I don't know. And then if it is a good change, like the number of uncovered interactions goes down, then maybe we want to accept that change and then try again, and then maybe change some other value. So the whole strategy is to make local modifications to the array to try to reduce the deficiency. Okay, so that's over the whole array, and I'm going to tell you right now, that's not very effective, because the problem is, if you're making a local change to the array, then it's very unlikely that you're going to make a very large change in the number of uncovered interactions, because the array is much larger than just, say, one position in the array. The other method, which turns out to be a little bit better, but it really depends on which method you pick. So some methods are better than others. The one row method is, we basically go in the way of density, but so then we make the one row at a time method, make one row, and then make local modifications to the row, not to the entire array. So this is more attractive because changing one element of a row is going to result in a bigger effect than a giant array like this. So one row is more attractive, but the problem is you can't modify earlier stuff. So yeah, so there are two different methods. I've actually tried both of them. One row is significantly better for some parameters, and it really depends on the algorithm that you pick, than the whole array one. The whole array is much easier to code, but the one row is usually better in terms of performance. So it's just something to keep in mind. Any questions on this? Okay, so what is a local change then? What we're going to call a move here is just standard terminology. In our terms, what we mean it to mean is changing the element of the array or the row or whatever. We're just changing an element to something else. That's all it means. You could generalize it by saying we're going to change 5 entries in this row, or change an entire row. And that actually is quite successful. But yeah, so a move is just what you define to mean what is a local change in the array. And the neighborhood is just what are the possible arrays you can get. So among all possible moves you can make, what are all possible arrays that you could make out of it? And if you perform a move, then either the deficiency goes up, stays the same, or goes down. It could really depend on which one you pick. So it's not always that if you make a move, you're always going to improve the array. You might actually worsen it. So now we just got to determine, well, if we improve the array, that's obviously a good thing. Well, if the deficiency stays the same, is that a good or a bad thing? And if the deficiency goes up, so if the deficiency goes up, then that's a bad thing that it looks like, but it turns out that it may be useful. So let's actually talk about a really simple algorithm first. So I think we talked about this one way earlier in the semester, but suppose that we have a hill to climb right here, and we're standing right here, and the only thing that we can do is we can make one step at a time and then maybe change our direction depending on what's happening. So if we're at the bottom of a hill or somewhere on the hill and we want to get to the top right here, how do we actually get there? So which direction would we pick?
Right.
Well, right, but what does that mean in terms of the hill itself? So let's actually look right here. So if we want to move right here or right here, which one of those two spots would you pick? The right one. Why would you pick the right one? Closer to the top. Another way to phrase it is it's higher than the one on the left. So what we can do is, well, we can move in the direction of improvement and never move in the direction of where we're not improving. So we just keep making local changes by going up the slope, so to speak, until we get to, let's just say we make a local change, we're right here, and then we make another local change, and we end up down here. So which one of those last two is better? The one that's very close to the top or the one further to the right? Which one of those two is better? Imagine that the one on the right is lower than the one on the top. Which one of those two is better? Yeah, the one on the top, because it's higher up on the hill. So we just keep making changes until we get to a point where we just keep searching and we can't find an improvement. So what do we do here? What we do is we just keep making changes to the array. If the array results in the deficiency going down, then great, we keep it. If the deficiency is going to go up, keep the original value there. So if we have some row right here where there's a 0 in it, and I say, no, I want that to be a 1 instead, but the 1 here makes the deficiency go down, which of the two values should I put there? Should I put a 0 there or make the deficiency go up? If the deficiency goes up, should I keep the 0 there or the 1 there? Deficiency is something we want to go down to 0. If the 1 makes the deficiency go up, which one should we keep, the 0 or the 1? Yeah, the 0, right. So if we put a 1 there, deficiency goes up, we just revert the change. And we keep the 0 there. But if the deficiency went down, then we keep the change, always. Okay? Any questions about that idea? So we're just going up the hill. Any questions about that? So why do you think I have or equal to bolded here? And if it's in bold, it's probably important. What if we made a change and the deficiency stayed exactly the same. Yeah, it doesn't seem to matter, but it actually is quite important. So why would I emphasize that here? So in terms of what we want, it doesn't change. Yeah.
It could just be like a plateau and keep going.
Yeah. So let's imagine this other scenario. So suppose instead of one hill, there are two hills. And we're standing right here. And actually, I'm going to, let's do this. So I'm going to make the second hill larger than the first one. So obviously, we want to go to the second hill. But if we just did hill climbing with where we are right now, where would we end up? Yeah, the first one, right. So we would just move up to here, but we would never get to the top of the second one. Why? We would move to the top of the first hill, but not the second one.
Won't go down.
Yeah, because we'll never go down. So why do you think I have or equal to here? So what this does is, I already have it here. It allows us to escape what are called local optima. And by that, it means, in terms of our picture, this allows us to instantaneously travel horizontally across the hills here to the same height, because the deficiency is exactly the same. So by making a change where the deficiency stays exactly the same, then we can transport over to another hill at the same height, and then maybe that's the way where we go to the top. So this idea of escaping local optima is really important in this area. And it's one of the reasons why this area has shown to be very fruitful for making covering arrays, because it allows us to escape local optima really easily. Any questions on that? Yeah.
How to make it so the algorithm doesn't stop once it finds a certain number of arrays that increase the efficiency for a certain number of iterations. Like you have to specify that a hard-coded specification for the iterations to stop, because like in that scenario, the efficiency would increase for a set number of iterations.
Yeah. So the way that you would implement this is, maybe after 100 tries of trying to change the deficiency, we can't improve it, then we just stop. So, and if we ever improve it, we reset the clock and then we just go again. So that's usually how it's done. Now, the problem is how many iterations are you going to put in? So that's obviously going to depend on the array that you pick. The usual way that people do this is they say that the number of iterations before quitting, they're going to set to be n times k times v. That's usually how it's done. And why do I say n times k times v? Well, what are the number of cells in the array? N times k, and the number of things for each cell is v. So this is just saying we're going to try all possible changes to one cell in the entire array. Now, here we're making a random change, so it's not necessarily going to do every single choice of possible changes. It may do some multiple times, but that's usually how people implement this. The problem is that hill climbing, I don't think, has ever produced the best known covering array. So it's only like a curiosity, and improving this in terms of hill climbing by itself is an open problem. So can we actually improve hill climbing beyond just the simple algorithm without resorting to any of the other algorithms we're going to do, which are better? The advantage of hill climbing is that it's really fast, but it's just not very performant in general. Okay, so the next one on the list is the Great Flood or Great Deluge algorithm. So the basic idea is very, very similar. I can't spell modified. If the deficiency is at most the threshold determined by some function, and we have to define what that function is, then we keep the modified array. So the thing is, we're going to have some kind of function right here, where on the horizontal axis is the number of iterations that we've done, and on the vertical axis we're going to plot f of x, and maybe it looks something like this. And what we're going to do is, at each moment in time, we're going to accept the array if we are below that function. So if we, for example, have an array that's right here where we made a change, then we're going to accept it. And if we, on the next iteration, make it worse, then we're still going to keep it because it's still below the blue line. And then if we want to have an array like right here, it's over the line, so we don't keep that change. And then we just keep going as long as we're still under the line. Okay, any questions on that? Yeah, so the key here, of course, is how do you design the function f here? So I'm not as knowledgeable of this as I should be, but the key here is trying to decide what the function is. How do you actually design the function? And one of the main issues with it is that it's absolutist. So it may be that in this plot right here, it may be that we do want to accept an array that goes over the line, maybe just for a little bit, but then ducks under the line after that. So maybe if we had accepted that change, maybe we could have an array that goes down to 0 like this. But if we didn't accept that change, then it would be much harder. So it's absolutist in the fact that if you're strictly under the line, we keep it. If we're strictly over the line, we don't keep it. So whenever you have these hard boundaries, when you're trying to decide whether to accept a change or not, this is usually a good sign that your algorithm is not very good. So the key here is maybe you want to accept some kind of tolerance of how many times we're over the line, or maybe something else which we're going to talk about, which is simulated annealing, which is kind of like this, but we'll talk about that in a second. But any questions on what the Great Flood algorithm does? So as long as you're under the line, you're good. If you go over the line, you don't keep that change. Okay. And then if you don't make an improvement after so long, then you just stop. Yeah.
How do you decide the setting configurations?
Oh, good question. I haven't talked about that. I kind of had it up here, which I didn't really talk about. So the usual way of doing things is you make the array completely at random because we don't know what it's going to look like. So you just make a random array, you just pick one at random, and then you just try to improve that array, usually. And so that's the whole array formulation. You just say, we have 100 rows right here, and we're just going to stick to 100 rows forever. And then we modify the array that we just happen to pick. The one row formulation is not exactly the same, but maybe you just pick the rows at random. That's another way that it could be done too. But the whole array one is if you have a certain budget of a certain number of rows, that one's a lot better. Whereas the one row one, you don't guarantee how many rows are made.
So the problem can also be impossible to solve.
It could be, yes. And that's so of course these methods don't prove that an array doesn't exist because we just may not be able to find one, but it's a very good heuristic as to when one actually exists. And in fact, the method that we're going to talk about next, simulated annealing, it has been proven that if you run simulated annealing long enough, it will reach the optimum for the parameters that you set. So if the array doesn't exist, asymptotically, the simulated annealing algorithm will never find it. And if the array does exist, the simulated annealing algorithm will find it. If you ran it for infinitely long, but of course you can't do that. Any questions on Great Flood or Deluge? Okay, so note that like the previous 2 slides had 4 bullet points and this one only has 2. So you may think, well, simulated annealing is not very important. There are hundreds of papers on simulated annealing for covering arrays. So don't be fooled by the fact that there are only 2 bullet points here. It's very important. It's a very important algorithm. And so basically, what's the idea here? So it's kind of like the Great Flood algorithm, but we're going to do kind of a hybrid of hill climbing and the Great Flood at the same time. So we're going to, again, have a function that goes down like this, just like the Great Flood algorithm. So something like this. And again, the horizontal axis is number iterations. And the vertical axis is the function f, so it's exactly the same as before. But here's the idea. What we're going to do is, if the deficiency improves, you always keep the change, always. But the thing is, what if the deficiency gets worse? So here's the idea. So if the deficiency goes down, then we keep the new array, of course. But if the temperature, whatever that means, is larger than a randomly chosen number. So what does that mean? So here, let's just say that 1.0 is right here. And what we're going to do is, let's just say at this point right here, the deficiency went up. So then we have to decide at this point whether or not to still accept the change. So we're going to pick a random number between 0 and 1, let's just say right here. And if the randomly chosen number is below the line, as a result of having the deficiency go up, then if it's below the line, we keep the change. If it's above the line, we don't keep the change. So in this case, because the dot is above the line, we don't accept the change. But if the dot was, say, down here, then we accept the change. So how is this actually done? Well, what we're going to do is we're going to get a new array. So we're going to, I'm trying to say things and write at the same time. So perform a move on A, the original array, and then if the deficiency goes down, then keep A prime, the new array. Otherwise, generate a random number. If the random number is below the red line, keep A prime, otherwise keep A. So if the deficiency goes down, we always accept the change, always. But otherwise, we generate a random number, and if the random number is below the red line, which is always going down, we're going to accept the change. If it's above the line, we don't keep it. So where does this come from? So how many of you have ever heard of annealing of metals? So if I have like a piece of metal here and I want to transform it into some shape, well, if the metal is cool to the touch, then do you think I can just like start moving it and it'll get to the shape that I want? Not really, because it might break, it's probably brittle depending on the metal. So what do? You heat the metal to a very high temperature, and then you perform big movements on the metal. You start hitting it really hard, and then it starts to form the shape. But as it cools down, we start making finer and finer adjustments to the metal as we're going. So that's where this comes from. So at the beginning, well, the temperature is really high. The red line is really high. So if we make a deficiency that goes up, very likely we're still going to accept the change, even if the deficiency goes up. But as the temperature cools down, we're accepting bad changes with less and less probability because the temperature is going down. Okay? So this has proved extremely successful. So if you want to introduce some kind of algorithm in whatever your project you're doing, this is an absolute great algorithm to pick because it has proven extremely effective. And as I was discussing earlier, it has been proven that if we run simulated annealing until infinity, the optimum will be reached. So if we run it for an extremely long time, we will get the optimum answer. That's actually been proven. So that's actually pretty amazing compared to the other two methods, which don't guarantee to get the optimum value. Whereas simulated annealing, you guarantee to if you run it long enough. So the questions for simulated annealing are, well, what is this temperature? How does it change over time? What do you start the temperature at? So that is a matter of huge discussion here. And there are some techniques where some of the time you have one particular move and some of the other time you have a different move. So there's a ton of research on this, so I'm not going to talk about everything there, but there's so much that you can do here. So if you want to incorporate simulated annealing into your project, that'd be a really cool thing to do. Okay, any questions about simulated annealing before we quit for today? Okay, so I'll see you on Wednesday. Remember, there are 2 papers that we are to read for this week.